Okay, so we are going to sketch that function f of x equal to x cubed minus 6x squared plus 5x. All right, so let's start with the shape. Now your shape, remember, it is determined by the coefficient of x cubed. If the coefficient of x cubed is positive, then you are going to start with the maximum. So your shape is going to look like that. Okay, because a is greater than 0. Okay, because a is greater than 0, your shape is going to start with a maximum turning point. All right, then let's find the x-intercept. X-intercept. Remember, you have to equate f of x to 0. Okay, for you to find the x-intercept, as always, like in the previous grade, you just equate f of x to 0. Right now, when you're in an examination situation, okay, if they ask you to sketch the graph, okay, the determination of the x-intercept, the coordinates of the stationary points, your point of inflection, and so on, okay, you can do it manually using the three methods, that is inspection, you can use inspection, you can use synthetic division, you can also use long division, but you can also use a calculator. Now, depending on the mark allocation, it's not necessary to use the manual ways. You can just use your calculator straight away. Okay, so for today, we are going to use the calculator to determine the x-intercepts. So I want you to tell me what are the x-intercepts there. I can factorize this as well. I can factorize this polynomial. But I want you to tell me using your calculators quickly the x-intercepts. The first one is x equal to what? 5. Okay, obviously there is x equal to 0. There is x equal to 5. Another one, x equal to 1. So those are your what? The x-intercepts. Okay, I just want to emphasize this, that the manual ways, okay, they are useful depending on the question. Okay, if the marks are going to be allocated for sketching the graph, how you determine the x-intercepts is not important. So you can use whichever method you like. Okay, if marks are going to be allocated for the x-intercepts on the graph, how you found those x-intercepts is not important. Okay, the most important thing is you must get them right. If you prefer the manual ways, it's fine. If you use the calculator, it's also okay. But remember, in an examination, you'll be working with time. So I suggest that if they ask you to sketch the cubic graph, straight away use your what? Your calculator to determine the x-intercept. Okay. Then the y-intercept. Remember, this one here, you can get it when x is 0. So for this question, y is going to be 0. Okay, y is going to be 0. Very straightforward. You don't need a calculator for you to find the y-intercept. Okay, what this means is that the graph is going to pass through which point? The origin. Okay, it means the graph will pass through the origin. All right. Let's move on to the next page. Okay, let's find the stationary points. Now, for you to find the stationary points, remember I told you that you need to find your first derivative. And then you must equate the first derivative to 0. The resulting equation is quadratic. And you taught quadratic equations from grade 9. Okay? So, we are going to end up using if f of x is equal to x cubed minus 6x squared, like I said, plus 5 there. So your first derivative will be equal to 3x squared minus 12x plus 5. So you now have a quadratic, it's more like it's a quadratic equation. Okay, but remember, for the first derivative, for you to find the x coordinate, you must equate it to 0. So 3x squared minus 12x plus 5 is equal to 0. Okay, again here, you can use your calculator, or you can use the method of completing the square. You can use factorization if it can be factorized, any other method that you know of. Okay, you can use the quadratic equation to get those x values. Okay, but I suggest that in order to save time, if the question is direct about the sketching of the graph, there are no marks on, or rather there will be no marks for how you determine the x values. Okay, so what are the x values? X equal to what?
3.527.
Okay, just give me to two decimal places.
3.53.
3.53 or
0.47.
0.47. Don't be surprised that the x-intercepts are decimal. Sometimes it is very possible. It depends on the equation. Your equation determines how the x values at the turning points are going to look like. Okay? Now, use these two values to find the y value. What is the y value when x is 3,53?
Minus 13.13.
Minus 13,13, like that, right? And the other one,
1.13.
1,13. Okay, so when x is 3,53, the y is minus 13,13. When x is 0,47, the y is 1,13. Okay, so you're going to have 2 points where the graph is going to turn. That is, one point you're going to have a maximum turning point, the other point is going to be a minimum. Okay, then let's move on to the point of inflection. All right. Already we know that the first derivative is 3x squared minus, it's minus what? 3x squared minus 12x plus 5. So all you have to do is find the first derivative of this function. Okay, by the way, remember, the first derivative of a cubic function is also a function. It's a quadratic function, which means you can sketch it. Okay? This f prime of x is the same as y. Okay? It is the same as y. So you can also sketch the graph of the first derivative of a cubic function. You can sketch it. Alright? So we are going to have f double prime of x will be equal to 6x minus 12. I'm sure you can see that the second derivative is a linear function. Again, this f double prime of x can be replaced by y, which means you can also sketch the graph of the second derivative of a cubic function. Okay? Because it's linear, and you were taught linear functions from grade 9. Okay? Now, once you find your second derivative, for you to get the x value at the point of inflection, you equate it to 0. So you end up having, say, x minus 12 is equal to 0. So 6x is equal to 12, which means x will be 2. So at the point of inflection, where the graph changes, for this question, the graph is going to change from being concave down towards being concave up. Okay, the concavity will change from being concave down, because there's a maximum turning point first, then followed by a minimum turning point. So the concavity will change from being concave down, concave up. Okay. At the point where the concavity changes, okay, the value of x at that point is a 2. Okay? So we need to find the y value at the point of inflection. Now you must substitute this x value into the original cubic equation. Please don't make the mistake of substituting into the first derivative or second derivative. You have to substitute into the original cubic equation. okay, to get the y value there. So if you substitute into it, what do you get? So, okay, what I'm gonna do, I'm gonna write my function as f2 will be equal to 2 cubed minus 6, am I right there? 6 times 2 squared, okay, minus, is it a minus or a plus? The plus 5. So I'll get 8 here, that's 24. So that will give me 8 minus,
That's 5 times 2.
oh, there's also 5x, so there's times 2 there, right, plus 10. So that this will give me minus 16 plus 10, you get minus 6. Okay, so at the point of inflection, x is equal to 2 and y is equal to minus 6. Okay, right. So let's sketch it. Okay, I'm going to sketch it manually, but from now on, after I sketch the graph, I'm going to use the computer, but using sketching this one due to my hand. Okay. All right. So I want you to guide me a little bit with some of the values. Okay. Our x intercept, what's the largest value?
5.
It's a 5. Okay. Since it's a 5, and our y-intercept is 0, am I right? What's the value of x at the turning point, the maximum? At the turning point, what's the maximum? 3,5. And the minimum?
0.47.
Okay. So my x value, maybe I'll just use 2, 4. So that's 6, and you can have 8, and then 10. On the other side, I'm going to have minus 2, minus 4, minus 6, minus 8. Okay, and then my y values, I want you to tell me what are the y values at the turning point?
13.13.
13.13.
Oh, sorry, minus 12.
Minus, and the maximum, what's the maximum value of y at the turning point? 1,13. Right. Okay. Right. First, I'm going to start with my x-intercept. Okay. I want you to tell me, I know that one of them is 0. Am I right? And then, can you tell me the others? There's 5, which is somewhere here. And there's positive 1. Positive 1. Okay, my graph is going to become very small. Okay, let me change my scale. Okay, let me change my scale. Because I don't want my graph to be very small. So I'll make this one 1, that one 2, 3, 4. Then we have minus 1, then minus 2. Okay? Okay, in most cases for you guys, they might give you a grid, but if they don't give you a grid, then you must choose a good scale. So we have x equal to 0, we have x equal to 1, and we also have x equal to 5. Okay? So I labeled the point where my x-intercepts are. Now I need to move on to the turning point. Okay? So I want you to tell me what's the first pair in terms of x and y at the turning point. What are the coordinates?
0.47.
0.47.
1.13.
1.13. Okay, let me calculate my my y. So my y, I'm gonna have 5 there, then I'm gonna have 10, and then 15. That will be minus 5, minus 10, minus 15. So we said we put 0.47 and what?
1.13.
1.13. So 1.13, I'm going to approximate it to be somewhere there. Okay? I'm going to approximate it to be somewhere there. Okay? I want you to be aware that it's because of the scale of my graph. Right? So what's the second set of coordinates?
3.53.
3.53.
Negative 13.13.
Negative 13.13. Alright, so I'm going to approximate it to be somewhere there. Okay, now this is very important. The moment you plot at the point where the x-intercepts are, the turning points are, before you even sketch the graph, okay, because of the shape which you are supposed to determine first. Remember, the shape says you must start with the maximum first, then the minimum. From what you can see here, it means that this point here, that's where the maximum turning point is going to be. And this point here is going to be where the minimum turning point is going to be. So the graph is going to start by being concave. Okay, by the way, the y-intercept is there. Okay, y-intercept is there. For this question, or for this equation, the y-intercept is 0. But it's not always the case. It can be at any other point along the y-axis. So, when I sketch it, okay, let me use that. Right? My cubic graph is going to look like this.
And the point of inflection?
Oh yeah, I forgot to put that point. Okay, the point of inflection, we have x equal to 2 and
Negative 6.
negative 6. So I can approximate it to be, I need to use another color for that. So our point of inflection is going to be somewhere here. Okay, somewhere there. This will be where your point of inflection is going to be. So your graph is going to pass through that point. Now, it's very important for you to include the point of inflection to help you in terms of the shape of your graph. Because if you don't include it, your shape won't come out nicely. Okay, so let me sketch it now. Remember, when you are sketching, it's freehand. My point of inflection, my other turning point has disappeared. Okay, so that's somewhere there, 3.53. I'll put it somewhere here so that my graph will look like that. And then it goes, and then it goes. Okay, so the graph will look something like that. Okay, it looks something like that. Now, your shape is very important because in most cases you get a mark for the shape. So the shape must be correct. All right? So the graph will look like that. Now, I just want to add, okay, here for some time. All right, I just want to add some things here now. Okay, I want you to put those as answers on your graph. Okay, so this is f of x. But sometimes you can get a question saying, for what values of x, okay, is the cubic graph, say, an increasing function? Okay, for what values is it an increasing function? But what I want you to do is on your graph, just write increasing, and then I want you to write your answers. Write your answers. And then we are going to discuss it. For what values of x is the graph increasing? Okay, now this is actually the beginning of interpretation. Okay, because you need to know how to determine those values of x. You can write your answers. If you are doubting yourself, you can write with a pencil. Okay, so we want the values of x such that this graph is an increasing function. Okay, now if you want, you can use the derivative, but it's not really important. Which two key points are you supposed to use in order to determine the solution of such a question? Use the turning points or the stationary points. Okay, so we know that the x value here is 0.47. To the left of this point, okay, the graph is an increasing function because the gradient is positive. So one of your solutions is going to be x is less than 0.47. Okay, so we're talking about to the left of the graph. Okay, to the left of the graph, it is increasing. The x values are those ones that are less than 0.47. Then, when it gets here, it starts to decrease, means the gradient is becoming negative. When you get to the turning point here, okay, the gradient becomes 0. After this turning point, it starts to increase. Okay, so we need the x value here, which is 3.53. So when x is greater than 3.53, the graph is an increasing function. Okay? Then, for what values of x is it concave down? Okay? Now, if you have been going over your work, last lesson I gave you inequalities. Okay, I gave you two inequalities, one for concave up and another one for concave down. Okay, I hope you have been going over your work. All right. Concave down, it means we have a maximum turning point. In the vicinity, there is a maximum what? Turning point. That's what concave down means. We have a maximum turning point, which is a set face. So in the vicinity of or we can say the vicinity of any value of x, we are going to have a maximum turning point. So, if you want, you can use the inequality that I gave you, or you can get the solution from the graph. Okay? The graph is concave down until you get to the point of inflection. Okay? Up to there, the graph is concave down. So your reference value is the value of x at the point of inflection. So any question asking you about concavity, the x value at the point of inflection must be part of the answer. It has to be part of the answer. Okay? So x value here is 2. To the left of x equal to 2, the graph is concave down. Okay? So you can just write the answer here. X is less than 2. Right. It might be a problem to memorize the inequality. Okay, so you can get the solution from the graph. If you decide to not get the solution direct from the graph, then you must use your second derivative. Remember, I told that if the function is concave down, okay, or the graph is concave down, your second derivative, okay, must be less than 0. You remember that? It's in your book. It's in your book. So what you do, so let me just do this. I'm going to erase it though. Okay? So what you can do, if you can't get the solution from the graph, you substitute, remember, f double prime of x is less than 0. So the linear function which you got after finding the second derivative, which was what? What was the second derivative?
6x minus 12.
It was 6x minus 12. It must replace f double prime of x. I'm showing you another way of getting the solution. Then you solve this inequality. It's a grade 10 inequality. Okay? So you end up having 6x is less than 12, therefore x is less than 2. Okay? So this solution here, uh, this solution is from the graph. Okay? And this one here is by calculation. Okay? It's very easy. Right? The same rules apply for concave up. So for concave up, it means in the vicinity we have a minimum turning point. So for all values of x that are greater than 2, the graph is concave up. Okay. So in an examination, if you just write the answer x is less than 2 for concave down, if the question is 3 marks, you deserve all 3 marks without any working out. You get your full marks. But if you can't determine it from the graphs, then use this inequality to help you a lot, to make things easier. Okay. Any question? Any question? If you don't have any question, then let me move on to another aspect. I want us to talk about the second derivative and the first derivative in terms of the graphs. Okay. I'll be able to explain to you how we come up with that equation. Okay? Okay. So the first derivative of a cubic function is quadratic. And the second is a linear function. Now, sometimes they can give you a question. In most cases, it will have a quadratic graph. And they can ask you from a quadratic graph to sketch the corresponding cubic function. So you need how to, you also need to know how to move from a quadratic function to a cubic. Okay, in most cases, it's the relation between the cubic and the quadratic. But you can also involve the linear function. Okay. So I just want you to write this down. For example, okay, I have a function here that's x cubed plus 3x squared plus 2x. Okay, x cubed plus 3x squared plus 2x. All right? So I'll just write here e.g. f of x equal to x cubed plus 3x squared plus 2x. Okay? Your first derivative will be 3x squared plus 6x plus 2. That's a quadratic. Okay? That's quadratic. The second derivative will equal to 6x plus 6. And that's linear. Okay? Now, we are going to sketch all three. Okay? I'm going to sketch all three, but I'm going to use a computer. Okay? Now, we are going to analyze the relationships. And then later, we can do a summary of the relationship. Okay? Make sure you pay attention. So, that's the cubic function. Okay, it has got a maximum turning point, then it has got a minimum turning point. So it's concave down, then concave up. Okay? This one here, it's concave down first, then it's concave up. Alright? Now, okay, this software it has got a slider. I need to change this. I think I need to change that equation. Let me put A there. Okay. Okay. Do you see that for the cubic function, if I put a equal to 1 here, you end up having a quadratic function. Okay. So let me change my slider now. Oh, in actual fact, I made a mistake there. Anyway, let me put x here. I'm supposed to have a x cubed like that. Okay. All right. So if your a is positive, like in this case it's equal to 1, you have the maximum turning point, okay, which is x cubed plus 3x squared plus 2x. Then if I move the slider, say to the left, okay, I can have something like that. I'm going to end up having a graph which is concave up and then concave down because the a value is now negative. So the shape change. The shape change from having a maximum turning point towards a minimum. Now we've got a minimum, then a maximum. Okay, so that's very important, knowing the effect of the value of a. Okay, I'm going to take it back to a equal to 1. Now, let me add now the first derivative. Like my first derivative, I'm going to call it g of x. Okay, so here you have your first derivative. I'm going to change the color there so that you can see it clearly. Okay, so you have your what? Your first derivative. It's quadratic. Right? First derivative is quadratic. Now, let me ask the computer to just add these points. We want the turning points, right, of the graphs. Those are the turning points, okay, of the two graphs. So you have your minimum and maximum for the cubic graph. That's the value. Now, your point of inflection, okay. The good thing is that this software, it can help me to determine everything. So that's my inflection point. I just need to put my function there. So my function is f of x. Okay. So the computer is also determining the point of inflection, which is that point. Okay? Now, by observation, what do you notice in terms of the relation between the two? I'm talking about, let's say, the x values of the two graphs. What do you see? The x values of the two graphs. Let me remove this keyboard. Right? The x values of the two graphs. What do you see? Yes, Tesha?
The x value of the turning point of the quadratic is the same as the x value of the x-intercept, the point of inflection.
Yes.
X value.
So the x value at the point of inflection is equal to the x point, at the point of inflection of the cubic graph is the same as the x value at the turning point of the quadratic graph. So if you are given the quadratic graph and they ask you to sketch the cubic, you need to know that, okay, my x value at the turning point of this quadratic graph is the x value at the point of inflection. Can you write that down? Write that down. So that's your first point. Yeah, okay, I want to write again just like relationship between quadratic or between the quadratic function or the first derivative and the cubic graph. You can decide how you want to write it down. It's your book. Okay? But what you need to know is that the x value at the point of inflection of a cubic graph is the same as the x value at the turning point of the quadratic function. In that case, the quadratic function is your first derivative. So write that down. Right. The other point which I want you to write for this graph, it's not very clear though, is that the x values at the turning point of a cubic function, please write that down. The x values at the turning point of the cubic graph, the x values at the turning point of the cubic graph are the x-intercepts of the quadratic function. So the x values at the turning point of a cubic function, those x values that you see at the turning point of a cubic graph, they are actually the x-intercepts of the quadratic function. Okay? Here it's not very clear, but they're supposed to pass, this line is supposed to pass through that point, and that one is supposed to pass through that point. All right? So make sure you are aware of that. Another thing, I'm sure you can see that here the graph is concave down. Do you see that the quadratic function, it's a decreasing function? So when the graph is concave down, always, okay, always, the first derivative must start as a decreasing function. The y values of the first derivative are decreasing, okay, when the graph is concave down. So the first derivative, which is quadratic, is a decreasing function when the graph is concave down. Okay. Now on the other side of the turning point of the quadratic graph, the quadratic graph is an increasing function. Okay, it's an increasing function, and the cubic graph is concave up. Okay, now let's change now the value of a from being positive, okay, even if I take it there, you're going to have the same scenario, okay, that I just explained. So you can see now when a is 2, it's not coming out very clear because this screen is not a little bit small. Now the graph is a decrease, the quadratic function is a decreasing function. I'm talking about when a is 2, right? It's 2 concave down. Okay? So when the first derivative is a decreasing function, the cubic graph is concave down. And then when the first derivative is an increasing function, the cubic graph is concave up. Okay, let's make it negative. If I make it negative, like that. Okay, I'm talking about the value of A, right? Now, the shape has changed. Okay, let me bring it down so that it can come out clearly. And then let me take that there. Right, now your cubic graph is now concave up, then concave down. Now, the quadratic, when A was positive, we had a minimum turning point for the quadratic. Okay, with the minimum turning point. But now A is negative, we now have the maximum turning point for the quadratic. Okay, so the quadratic is an increasing function. Okay, is an increasing function when the cubic graph is concave up, which is also true when A was positive. So when the first derivative is an increasing function, the cubic graph must be concave what? Up. And when the first derivative is a decreasing function, the cubic graph must be concave down. Always. That's very important, because if you are given a question with the quadratic graph with no cubic graph, if you are asked to sketch, you need to know how the cubic graph is going to look like from the quadratic. And it can be a bit confusing. So make sure you take note of this and you write it down. Because sometimes you might not have it in textbooks. What I'm telling you now, it's probably not in textbooks. You might not find it in some textbooks. Okay? So, when the quadratic or the first derivative of a cubic function is an increasing function, the cubic graph will be concave up. When the first derivative is a decreasing function, the cubic graph will be concave down. Okay? All right, let's move on to, let's add the second derivative now. The second derivative. So my second derivative, I'm going to call it h of x. Okay. H of x. In fact, let me call it h of x. H of x, that will be derivative. Now, in this case, it's going to be I'll put the derivative of the quadratic to make it linear. So it will be g of x. Okay, so you have that. The one in red. Let me make it bolder. Right, I want you to be aware that for this graph here, when a is -1, the point of inflection has changed. Okay, it's now at x equal to 1 and y equal to 4, which is this point here. All right? I hope you can see that. Okay, now, what do you notice in terms of the three graphs? Do you see something which is common here? Yes, then.
The x-intercept of the second derivative is equal to the x value of the point of inflection and the x value of the turning point of the quadratic.
Right, now here, the x-intercept of the second derivative, this is very important. The x-intercept of the second derivative, okay, is the same as the x value at the turning point. It's also the same as the x value at the point of inflection of the cubic. So the x value the x-intercept of the first derivative is the same as the x value at the turning point of the quadratic. It's also the same as the x value at the point of inflection. Okay, so sometimes if they give you a linear function and they ask you, well, what's the value of x at the point of inflection, you can determine it. Okay, if the graph is there. Okay, please write that down. The x value, or rather the x-intercept of the second derivative is the same as the x value at the point of inflection and at the turning point of the quadratic function. You can use it your own words. The x value here, this is the linear. The x value there, that's the quadratic. So this is the cubic. That's the point of inflection, and that's the turning point of the first derivative. Now, I want you to check this now. Remember, if you were listening carefully, or if you went home, you listened to the video, one of the videos, I think it was the one on point of inflection. And I want you to pay attention carefully so that you know where the inequalities come from. Now, do you see that the linear function, okay, in the fourth quadrant, it's what? Positive. The y values. I'm talking about the y values. The y values of the linear function in the fourth quadrant, they are what? They are positive. Okay? And in the fourth quadrant, the cubic graph, okay, I'm going to remove the in the fourth quadrant, listen carefully. In the fourth quadrant, y is negative. So for the second derivative, the y values are negative.
The y values are negative, right? They're not positive. Because you said positive first and then now you changed it to negative.
Maybe it was a mistake if I said that. So I'm going to correct it now. Yeah, I'm going to correct it now. In the fourth quadrant, y values are negative. Okay? The y values are negative. Which y values am I talking about? The y values of the second derivative, which is a linear function. They are negative. Okay? Now, do you see that our cubic graph is concave down? So when the y values of the second derivative are negative, the cubic graph is concave down. That's why I can write f double prime of x is less than 0. That f double prime of x, it represents what? Y. So what this means is the y values of the second derivative, when it's concave down, they will be negative. I hope you are following. So this is where the inequality originates from sketching. Now, and then in the first quadrant and in the first and in the second quadrant, the y values are going to become what? Positive. In the graph, as you can see, you see from just after this point to the left, it will become concave what? Concave up. That's why we can write, for that interval, we can write f double prime of x is greater than 0. So when the y values of the linear function are positive, the cubic graph will be concave up. Okay? Now let's change. Remember, we are talking about a case here when a is negative. Let's make a positive and see what happens. The linear function is going to change, the shape will change. See that? So what happened? We had a negative gradient when the a value of the cubic graph was negative. Okay? Now the a value is positive. We now have a positive gradient for the linear function. And our cubic graph is going to be concave down, then concave up. Okay? Now, if you look at the y values, okay, in the third quadrant, they are negative, and the cubic graph is concave down. So, if double prime of x is less than 0, when the graph is concave down. Okay? Then, As the y values become positive, I'm talking about the y values for the linear now. As they become positive, the cubic graph becomes what? Concave up. That's why we write f double prime of x is greater than 0. Okay. Right. So I'll see you. But I'm gonna give you homework, but I'll send it on the WhatsApp group. Okay, on sketching.